So what everything we learned in 7.1, which is pretty cool about those various Laplace transforms, if you just reverse that, we get the inverse. So if you go from left to right from the previous section, then the inverse would be just basically going from right to left. So we take the result and to try to get back to the form. Now, why is that important? Well, here the goal for this chapter is to Antonio. Um, you're recorded live, and your name will go throughout all eternity now. um, those guys are having a good time back there. What was I saying? Oh yeah. This chapter, the goal will be to solve a differential equation using Laplace transform. So that's going to be our goal. In section, I don't know if it's 7.2, but I think at the end of 7.2, we're going to take a problem, a regular differential equation problem, solve it using Laplace transform. So we should be able to show you that. And then I thought I had one more day, but I forgot we missed the day, and then we had a weather day. And so on that day, I wanted to get into really just one application problem to kind of show you some things. If I have time, which at this stage I just hardly don't have much time for anything now, I could maybe try to put that problem in a video and just post it out there for you. But it's a really neat application to where all this stuff, fits into. It kind of sheds some light on the value of the Laplace transform. So if I can post it out there, I try my best to. So let's see. So if you look at this theorem, you remember in the previous section, they had things like the Laplace transform of something like the Laplace transform of 1, and that gave you 1 over s. So indeed, if you take the inverse transform of both sides, then you just get the reverse, and that's part A right here. So, and all the way through, these inverse transforms just comes from the idea that if I know the Laplace transform of 1 is 1 over s, so if I take the inverse transform of both sides, so here the inverse Laplace transform of the Laplace transform is just 1, that inside function, and so that's the inverse transform of 1 over s. And that's the case for all of them. So if we know that we have the Laplace transform of t to the n, and that's n factorial over s to the n plus 1. So if we take then the inverse transform of both sides, this is the inverse transform of the n factorial over s to the n plus 1. And so the inverse transform of the transform is just t to the n. And that's the case for all of them, right? So with that in mind, let's work a few problems. So when you look at this, you want to first try to think, where is this coming from? So if we recall the Laplace transform of t squared, that this is 2 factorial, which is 2, all over s to the third. But the problem that we have here doesn't have a 2 there, so 1 over s to the third. So if we take this same problem that we're working with and here just divide both sides by 2, we have 1/2 times the Laplace transform of t squared is equal to 1 over s to the third. So if that be the case, then the inverse transform of 1 over s to the third is 1/2 times t squared. The inverse transform of the 1 over s to the third gives us the 1/2, and taking here the inverse transform of that 1/2 is still, that's just 1/2, and the inverse transform of the t squared is 2 over s to the third, and then times the 1/2, and so we get what we need. So this guy here is the 1/2 there times t squared. Let's look at this one. You break this down. This is the inverse transform of 1 over s squared minus the inverse transform of 48 over s to the fifth. Well, you recall that the Laplace transform of t is 1 over s squared. So that first one is just t. But now that next one, we look at the Laplace transform. You know, n here is going to equal to 4. So we look at the Laplace transform of t to the n, well, t to the fourth, excuse me. Well, this is 4 factorial over s to the fifth. Well, 4 factorial is 24 over s to the fifth. But this problem has 48. Well, no problem. So we come back. This is the inverse transform of that 1 over s squared minus 48 is no more than this 2 times 48. Well, 2 times 24, excuse me. So this is 2 times the inverse transform of 24 over s to the fifth. So the inverse transform of 1 over s squared is just t. And then the inverse transform of 24 over s to the fifth, well, that guy is t to the fourth times the negative 2. So it's minus 2 times t to the fourth. So all we're doing leading up to how to solve a differential equation using the Laplace transform is that we're actually going over all the properties that put all the pieces together for solving a differential equation using the Laplace transform. And you'll see, as we go further, you'll definitely see the pattern would display itself better and better. My grandmother used to quilt quilts, and that's what I remembered her as a boy. And so in the dining room, my granddaddy had put 4 nails in the corners of the ceiling, and so he had a drop string, and so he had also built these poles that had holes in them, and so he would connect and make a square, and then my grandmother would take her quilt pattern, and she would lay there the bottom piece, and we had to beat cotton. That was the thing, man. It was funny. They'd go get cotton and bring cotton in that room, and they had this long stick, and they would beat the cotton for whatever reason, right? Make it, soft and that kind of thing. And sometimes you had some seeds in it. They'd try to get some of the seeds out, whatever, that if the cotton gin didn't get that out. They put that cotton, spread that out in that inside layer, and then she'd put her pattern pieces on top. But then every day she would quilt, and she would quilt that whole thing. And sometimes it didn't really make sense from the beginning, but as time progressed, oh man, it really made, it was very clear how pretty, the pattern would show up. That's what we're doing here. So now we're getting the nails, and you're saying, why are we putting nails up here in the ceiling, right? And then we're gonna get these poles. Why are we getting these poles, right? And then we're gonna beat some cotton. Why am I beating cotton? But then after a while, we're going to put this pattern together. It's going to be a very pretty, nice quilt. I don't know if you all have heard anything about the quilting bee down in Gee's Bend, Alabama. Have you all heard of that? It's been on national news, and they've done documentaries on that. And but that's just a few miles from where I'm from. Gee's Bend is a little bit south of Oroville. They're in Dallas County, drop down below that to Wilcox County. My grandfather was born down there on a Mennonite plantation, and so right above where my folk came from. So and my grandmother used to work with those ladies with that quilting bee. So yeah. Anyway, so we're just putting the pieces together for a very pretty pattern that we'll show. Was any questions on that previous one? I'm sorry. Let's look at another one. So we're making use of the inverse Laplace transform. With something like this, notice that in order to get the transform, I have to be able to break down this expression. One of our best tools of breaking this down is partial fractions decomposition. And you thought you had rid your whole life of partial fractions decomposition, right? So we take that s plus 1 to the third over s to the fourth, and we list out its generic partial fractions. So we write this as a over s plus b over s squared plus c over s to the third plus d over s to the fourth. You write your denominator in that ascending order when you have repeating terms, right? Sometimes you're used to seeing terms in your denominator as being factored, like let's say x minus 1 times x plus 2. So you'll write a over x minus 1 plus b over x plus 2. Because they are said to be distinct roots, distinct terms, you list them like that. But if they're repeated roots, s is being repeated now in your denominator 4 times. So it's basically that term in your denominator to the nth power. So it becomes a over s to the first plus b over s to the second plus and so on plus some whatever is p coefficient over that s to the nth power. And so we list the terms out in this fashion. Multiply both sides by LCD, which is s to the fourth. So we end up with s plus 1 to the third is equal to as to the third plus bs squared plus cs plus d. You use the binomial theorem to expand s plus 1 to the third. This is s to the third plus 3s squared plus 3s plus 1. That's equal to as to the third plus bs squared plus cs plus d. And then all of math tends to work together. That's what Paul meant when he said that all things work together for good. You didn't know he was talking about math too. Yes. Oh man, I'm getting happy. Anyway, so so you look at this is the equal sign. Left side has to equal the right side. So the corresponding parts must also be congruent. So that means that the coefficient for s to the third has to be the same coefficient for this s to the third. So we see the connection for all 4 of them, right? That a is equal to 1, b is equal to 3, c is equal to 3, and d is equal to 1. As Miss Anderson up in Indianapolis when I was a boy, she would always say to us, "How about that there? How about that there now?" You know, country folk. So is everybody with me on that? Okay. So what we do is we go back to the problem. Pull this down. I need more space. So this problem is the inverse transform of this s plus 1 to the third over s to the fourth. That's equal to the inverse transform of all the parts. So this is a over s, where a is 1. So this is 1 over s. B is plus 3 over s squared, plus c is 3 over s to the third, plus d is 1 over s to the fourth. Well, you could break those into their individual parts as well. So this is the inverse transform of 1 over s plus 3 times the inverse transform of 1 over s squared. I'll just pull that 3 out in front. And plus, now here I get into an issue because this is s to the third, n is equal to 2. So I need to have 2 factorial up top. So I don't, so I place it there by saying 2 divided by 2. So here I pull the 3 out, divided by 2, times the inverse transform of 2 over s to the third. This is 2 divided by 2, just a sophisticated 1. Plus this s to the fourth, n is equal to 3. So I got to have 3 factorial 6 up top. I don't. So 3 factorial 6, so I have basically 6 divided by 6. So I have 1/6 times the inverse transform of 6 all over s to the fourth. This is that 3 factorial. Need more space. So now we can write the answer. The inverse transform of 1 over s is just 1 because the Laplace transform of 1 is 1 over s. So this is 1 plus 3 times the inverse transform of 1 over s squared is just t plus 3/2 times the inverse transform of 2 over s to the third. It's just t squared because n is equal to 2. Then plus 1 over 6 times here, n is 3. This is t to the third power. Okay. Is everybody okay with that? So we can break this number 7 down into its parts as well. This is the inverse transform of 1 over s squared minus the inverse transform of 1 over s plus the inverse transform of 1 over s minus 2. Well, the inverse transform of 1 over s squared, well, that's just t. The inverse transform of 1 over s, that's 1. It's a minus here, so it's minus 1 plus the inverse transform of 1 over s minus 2. Well, that comes from the Laplace transform of e to the 2t, right? So this guy is just e to the 2t. Now this number 9 is tricky. It's tricky because the form that we are comparing this to is the Laplace transform of some e to the at. Now watch how that's written. This is 1 over s minus a. Well, we can fix the minus sign by just making that a minus a, and then we've got a plus sign there. But it's supposed to be nothing associated with this s except the coefficient for 1. But this guy has a 4 sitting right there. So we just factor out that 4 from our denominator. So this guy is 1/4 times inverse transform 1 s plus 1/4. And that becomes 1/4 times e to the negative 1/4 t. Is that okay? Okay. All right. Now number 11 and number 13, you see that s squared down there? It's like s squared plus a square. And this is a s squared plus a square over 1. Then you want to think in terms of either cosine or sine. So we go back and look at those forms, the Laplace transform of cosine kt. But this guy is s over s squared plus k squared. Then the Laplace transform of sine kt is a k all over s squared plus k squared. Now, if there's a number up in our numerator, then you always think sine. Okay? If there's an s up top, then you think cosine. There's an s here in number 13, so we think there's some kind of form of cosine for that answer. So the only problem with the k being up in our numerator is that this k comes from this term here, that k squared. Well, the k here is 7. There is no 7 there, so I put it there and then I divide by it at the same time. So here, k is equal to 7. So we're going to write this. We pull the 5 out. This is divided by 7 times the inverse transform of 7 all over s squared plus 49, or 7 squared. And so this looks directly as sine of 7t times on the outside 5 over 7. So this is 5 over 7, your k term, so that's sine 7t. Okay? Let's look at this one. This guy, we said that since it has an s up there, so it's going to be some type of cosine, but I get two things that's in the way. It's a 4 in front of that s, and there's a 4 in front of this s squared there. So what I'm going to do first, let's take out this 4 from the numerator. This is 4 times the inverse transform of s all over 4s squared plus 1. And just like we did with a couple of problems before, we got to factor out a 4 from our denominator. So this is 4. I'm going to factor out, let's just write it like this for right now, 4 times the inverse transform of s all over. Take out a 4, so this is s squared plus 1 over 4. Now I can pull this 4 out, so that's 4 divided by 4, that cancels out. So this is just the inverse transform of s all over s squared plus 1 over 4. Well, here, our k is 1/2. Right? So we square that, we get the 1/4. So here, this is the cosine here of 1/2 times t over 2. Okay. Any questions there? All right. And look at number 15. This guy has 2 terms in our numerator. So we got to break that down as it is. So we're going to write this as 2 times the inverse transform of s over s squared plus 9. And that's minus 6 times the inverse of 1 over s squared plus 9. So here our k is equal to 3. Well, that first guy is just cosine. So this is 2 times cosine of k, which is 3 times t, minus. Now for the sine, I got to have that k term up in the numerator. Well, here k is 3, right? Well, I can borrow 3 out of that 6 right there. And so we can write that as 2 times the inverse transform of 3 all over s squared plus 9, and then you get what you want. This is 2 cosine 3t minus 2 times sine 3t. Now, do you see where, if you recall in some of our problems back in chapter 4, we had the complementary solution coming out to be a combination of a sine and a cosine. It's like c sub 1 times cosine x, and then plus c sub 2 times sine of x. But this is what we're trying to build. So this is actually some type of solution. We'll work a problem in just a minute where we get solutions like that, and we can use Laplace transform to be able to do it. The neat thing about the inverse transform is that once you're solving a differential equation using Laplace transform, once you get everything down, you're going to have some Laplace transform, but to get the answer in terms of what you are familiar with, going back to like, okay, y is equal to, or y sub c or y sub p, we have to take the inverse Laplace transform to be able to get that. Right? So we're just doing the baby steps to show you how to piece everything together. All right. This guy right here, the only way to break down that s squared plus 3s in our denominator is to somehow we can get some fractions, some partial fractions there. So we'll use that method for this one, partial fractions. So we have 1 over, this is s times s plus 3. This is a over s plus b over s plus 3. Multiply both sides by the LCD. We get 1 is equal to a times s plus 3 plus b times s. So if you let s equal to 0, a is equal to 1/3. If you let s equal to -3, then b is equal to -1/3. So this problem becomes now, it's the inverse transform of that a, which is 1/3 over s, plus -1/3 over b, which is, well, its denominator, s plus 3. So we can write that as 1/3 times the inverse transform of 1 over s minus minus 1/3 times the inverse transform of 1 over s plus 3. Well, the inverse transform of 1 over s is just 1, so this is just 1/3. And this is minus 1/3 here. And then this inverse transform of 1 over s plus 3 is e to the -3t. E to the -3t. Is that okay? So we have to use partial fractions for this one as well. So this is S over, if we factor this, this is S minus 1 times S plus 3. So this is A over S minus 1 plus B over S plus 3. Multiply both sides by the LCD. This implies that S is equal to A times S plus 3 plus B times S minus 1. So if I let S equal to -3, so I get -3 is equal to A times -3 minus 1 is -4. So that implies that A is equal to 3/4. Then if I let S equal to 1, so I get 1, excuse me, what did I do? That's B. We let S equal to -3, then that's -3 is equal to, that A cancels out, that's B. Sorry. So here we let S equal to 1, that cancels out the B, so we have 1 is equal to A times 4, so we get 4A, and that gives us A is equal to 1/4. So this problem is the inverse transform of A, which is 1/4 over S minus 1, plus the B, which is 3/4 over S plus 3. So this is 1/4. Then the inverse transform of 1 over S minus 1 is e to the t plus 3/4, and this is e to the -3t. Is everybody fine with that? Well, I think now we're ready to look at a problem where we can actually try to solve a differential equation using the Laplace transform, just in a very, very basic presentation. To do that, we need to be able to talk about the transform, taking the Laplace transform of a derivative, because in a differential equation, you're going to have a derivative. So how do we break that down? Well, here's the method based on this theorem. The theorem says that let f and its derivatives up to n minus 1 derivatives here be continuous on some interval closed from 0 to positive infinity, and are of exponential order. That is, that the so-called solution types will be exponential. So they're kind of begging that the problem is a differential equation with constant coefficients. Because of that particular differential equation, your solutions came out to be exponential order. So that's what they're claiming here. And are of exponential order, and if here this nth derivative of f at t is piecewise continuous on the same closed interval from 0 to positive infinity, then the Laplace transform. And you know, the idea of piecewise continuous is that it might not be continuous everywhere. Right? So it may be continuous on certain intervals, which is fine. If you claim that this function is continuous here, but it's not continuous somewhere else. That's important, because typically when you're taking the Laplace transform of a differential equation, a lot of times it's a signal equation where the signal turns something on, it's continuous. Then it turns something off elsewhere at another time interval, is discontinuous. So we only take the differential equation to find the solution. That is sometimes to find the amount of current, the charge, if it's an electrical current. I mean, it could be fluid flow as well. Where's the shut-on valve or shut-off valve? Where does that occur? In any type of fluid that you're dealing with. And so you can calculate the amount of fluid over a certain period of time. And so that's why they claim that the function or the functions here, this derivative, may be piecewise continuous. It may not be continuous in certain parts. That's okay. So here, the Laplace transform of the derivative, this is the some function with the nth derivative. So we note whatever n is. So here, if n, we're going to write this out as s to the n. This capital F of s is a Laplace transform. Capital F of s is just equal to the good old-fashioned Laplace transform of f of t. Just one way of writing it. So this is s to the n times the Laplace transform minus, so here the s's, their exponents will be counted in decreasing fashion, and then the initial conditions will be counted in increasing fashion. So think about it. This is s to the n, then minus s to the n minus 1, minus s to the n minus 2, until the s's will go out. You end up with s to the 0, which is just 1. But as you do that, notice that the initial conditions, and these are all initial conditions here, is times f of 0, that's the initial condition. The initial condition for the first derivative, that's f prime. Then you're going to go up to f double prime of 0, and so on. Now, the only thing about this is that the initial conditions here must all be, initialized at 0. Now you can get some term, you can get some value for that, that's fine. It could be f prime of 0 may equal to 2, that's okay. But we examine the initial conditions, and so you gotta have a problem with the initial conditions to be able to actually solve based on Laplace transform. Where's the problem? Here's a very simple problem. I'm going to work it using Laplace transform, then I'm going to also go back and work it based on what we did back in chapter 1, chapter 2, whatever. And you can see the comparison. So this is y prime minus y is equal to 1. We take the Laplace transform of this entire equation. So this is the Laplace transform of y prime minus y is equal to the Laplace transform of 1. You can do that because the Laplace transform is a linear algebra. So we get a lot of neat properties if something is a linear algebra. Matter of fact, because it's a linear algebra, you can break this down as the Laplace transform of y prime minus the Laplace transform of y. The Laplace transform of 1 is equal to 1 over s. Right? Now, according to that theory that we just looked at, this Laplace transform of y prime, y to the first, where n is 1, this becomes s times f of s minus, this is s to the first, so that next will be minus s to the 0, which you don't even have to write that. And this is times, and if it's okay, since they're using y, I'm going to use y as well. And so that, capital Y is the same thing here as capital F. I'm going to use y of s. This is times y of 0. Well, there's no more there. And this is minus the Laplace transform of y we just call that capital Y of s. This is equal to 1 over s. This y of s simply means that's the same thing as the Laplace transform. So this is s times y of s minus this y of 0 minus y of s is equal to 1 over s. Well, they give us that initial condition for y of 0 is equal to 0. So this is s times y of s minus y of s is equal to 1 over s. You can factor this y of s, and we have left s minus 1 is equal to 1 over s. Get the y of s by itself. This is equal to 1 over s times s minus 1. Again, y of s is the Laplace transform of y of t. This is equal to 1 over s times s minus 1. Here I take the inverse transform of both sides. When I do that, I just get y of t, this inside function, is equal to the inverse transform of 1 over s times s minus 1. We use partial fractions to break this down. So this is 1 over s times s minus 1 is equal to a over s plus b over s minus 1. Multiply both sides by the LCD. I get 1 is equal to a times s minus 1 plus b times s. This implies if I let s equal to 1, I get b is equal to 1. And if I let s equal to negative 1, if I let s equal to 0, I'm going crazy, let s equal to 0 to cancel out b, then I get a is equal to negative 1. So I have this y of t is equal to this inverse transform of this term here. Well, it's the same thing there, which is the same thing there. So now I know what a and b are. So this is the inverse transform of a, which is that negative 1 over s, plus the inverse transform of b, which is 1 over s minus 1. Well, the inverse transform, let's pull that negative. You can pull that negative out in the front. So you can write this as y of t. This is equal to that negative 1 times here the Laplace, the inverse transform of 1 over s is just 1. So this is just negative 1 plus here the inverse transform of 1 over s minus 1 is e to the t. Now, let me write the original problem. This was y prime minus y is equal to 1. Y prime minus y is equal to 1. And then we had y of 0 is equal to 0. Well, this is a differential equation with constant coefficient. So my auxiliary equation is y minus 1 is equal to 0. That gives me, excuse me, too much. It gives me m is equal to 1. So that means that y sub c is c sub 1 times e to the 1t, or just t, right? Now, for y sub p, I look at this term here, that g of x is 1, so I let y sub p equal to a. Take its derivative, I get 0, right? There's only one derivative there, so stop there. So I replace y prime with 0 minus, I replace y with a is equal to 1. And so here I get a is equal to negative 1. That is y sub p is equal to negative 1. But oh yeah, we had an initial condition. I forgot about that. So we take the initial condition coupled with y sub c equal to c sub 1 times e to the t, right? And let here y is equal to 0. That's equal to c sub 1 times e to the 0. Well, that implies, that's supposed to happen. It's supposed to be a plus a constant over there. Y sub p is equal to -1. That gives us that. We're looking for this c sub 1 there. C sub 1 is not 0. C sub 1 is equal to 1. Here t is equal to 0. That's right. What am I missing? Y of 0 is equal to 0. Oh. I almost lost it, but I'm fine. This guy is supposed to be here. I need to put in that y sub p as well. Okay. This is y is equal to y sub c plus y sub p. So y is equal to, here, c sub 1 times e to the t, and then that's -1, because y sub p is -1. That's better. So now, y of 0 is equal to 0. That implies that 0 is equal to c sub 1 times e to the 0 minus 1. That implies that 0 is equal to c sub 1 minus 1. That implies that c sub 1 equal to 1. I forgot my y sub p. Yeah. So here, y of t is equal to the c sub 1, which is 1, times e to the t minus 1. And the problem, the way they wrote the answer here is just put the -1 first, plus e to the t. Okay, so the idea is that you're doing the same thing. Now, you may say, hey, if I have a problem like this, then I'd rather work it based on what we did back in chapter 1, chapter 2, by all means, because that would be a whole lot easier than doing the Laplace transform. The differential equations that you would typically run into would be difficult, and so it would be easier to use Laplace transform. Because you remember some of those problems back before, depending on the nature of g of x, to get the value for y sub p, it could be very difficult to break that down. Or even using, you remember the method, solving the differential equation, using variation of parameters. That's a very long, tedious process as well. Eventually, you will see that the Laplace transform method is the so-called desired method. It worked this one right here, and then I want to go into 7.3. So here, we take the Laplace transform of everything, plus put the 5 in the front. Five times the Laplace transform of y prime plus 4 times the Laplace transform. That y is equal to the Laplace transform of 0. So this first guy, this is s squared, taking the Laplace transform of a derivative, times y of s minus s its exponent is descending times the first initial condition, and then minus here s goes out, the next initial condition, as I count up its derivative. So that guy covers that for that y double prime plus 5 brackets. This here is the transform of a derivative. This is s times y of s minus s goes out. All I have here is just y of 0. Close that up. Plus 4 times here y of s. That's just the Laplace transform notation for that is equal to 0. Now let's plug in those initial conditions. This is s squared times y of s minus y of 0 is 1, so this is just minus s, minus y prime of 0, that's 0 right there, and then plus 5s times y of s minus 5 times y of 0 is 1, it's just minus 5, plus 4 times y of s is equal to 0. Factor, get the y of s's together. I have left, that's the x squared plus 5s plus 4. Get everything else on the other side. It's a plus s over here and a plus 5. Get the y of s by itself, and when I do, this is s plus 5. Take that term in the brackets. We're dividing it and just factor it as we do. This is s plus 4 times s plus 1. Right. Take the Laplace transform of both sides, and I get y of t. The answer is the inverse of s plus 5 all over s plus 4 times s plus 1. We use partial fractions to break that down. S plus 5 over S plus 4 times S plus 1 there. So this is A over S plus 4 plus B over S plus 1. So I get S plus 5, multiply everything through by the LCD, S plus 4 times S plus 1. Have left A times S plus 1 plus B times S plus 4. Let S equal to -1, that'll cancel out this A. So I get -1 plus 5 is equal to B times -1 plus 4. So that gives us 4 is equal to 3B. B is equal to 4/3. Then let S equal to -4 to cancel out that B. So I get -4 plus 5 is equal to A times -4 plus 1. So we get 1 is equal to -3A. And so A is equal to -1/3. And you can always stop me if my algebra, my arithmetic goes in the ditch. Sometimes I get drunk in mathematics. I don't drink, but I get, you get drunk in math and then you write the wrong number, right? Okay, so let's see what we have. This is y of t, looking at this guy right here. That's equal to the inverse transform of the A, which is -1/3, and that's over S plus 4. plus the inverse transform of b, that's the 4/3 over s plus 1. So you can pull that negative 1/3 out in the front, so we get y of t is equal to negative 1/3 times e to the negative 4t plus the 4/3 here, pull that out in the front, times e to the negative t. Now that makes sense. Let's go back and look at the original problem. That's y double prime plus 5y prime plus 4y. What did I say? Plus and plus. Plus 5y prime plus 4y equal to 0. Its auxiliary form is m squared plus 5m plus 4 equal to 0. If you can factor, let's factor. M plus 4 times m plus 1 is equal to 0. So you get m equal to negative 4. See that negative 4t there. And then m equals to negative 1. That negative t right there. So y sub c is c sub 1 times e to the negative 4t plus c sub 2 times e to the negative t. You see how the Laplace transform is also solving the problem with the initial conditions? Because you plug those in there when we're doing the times y of 0 and the y prime of 0. Right? Good. Any questions there? I want to take 10 minutes and give you a really good introduction to 7.3. 10 minutes to introduce 7.3.